composite is generally a linear combination of variables. The graphical model shows this relationship. We have the observed variables, here the x's, x1, x2, x3, characterized by rectangles. We have the composite, which is characterized by a hexagon, a way of representing composites suggested by Grace and Bollen in 2008. And the relationships between them are characterized by weights, W1, W2, W3, and these are characterized as lines pointing from the observed variables to the composite. So what are they used for? When do we reduce observed variables into one composite? We'll see that there are various forms of composite, various fields of application. A very simple one, a very classical one in the psychology and other fields of social science are sum scores, average scores. Then we have item parceling. We have collections of heterogeneous causes. We have formative constructs. We have aggregate constructs. And we have indices. In the next slides, we'll have a look into each of these fields of application. The sum score is a special case of a composite, namely one that is created as the sum of a set of variables. So when we look at the graphical representation, we see that all weights are essentially fixed to the value of 1. Sum scores are very popular in social sciences. They have been classically a workhorse in psychometrics, and authors like Nonelli regard them as one of the most important psychometric means. Although we should be careful, this was a statement from the 1970s, but still practices that were recommended in those years are still heavily used even today. And so we find that in many disciplines, in particular applied disciplines, like for instance information systems research, marketing, business, and so on, sum scores are still heavily used. Another possibility very closely related to sum scores are average scores. Average scores are created by dividing every weight through the number of observed variables. So instead of using a weight of 1 for every observed variables, we use 1 divided by the number of observed variables. And the nice advantage of this approach is that then the variance of the composite, it becomes very similar to the variance of the indicators. In particular, if you use always the same scale for every indicator, then the composite will have the same scale than the observed variables. Indices are another field of application of composite. An index aggregates the information from multiple simpler variables. We have some concrete examples like the Human Development Index, Commitment to Development Index, the Gender Inequality Index, or the Gender Gap Index. Moreover, there are many stock exchange indices, indices that express the investor sentiment in a certain market. Or there are price development indices, which are constructed by national statistics offices to determine the inflation rate in a country. Indices are usually something which is practical. It's not necessarily about mirroring a variable that really exists, but it's rather about condensing information in several variables into one single variable. Another field of application of composites is item parceling. And item parceling is an approach to cope with larger scales that consist of many observed variables, and these observed variables are originally meant to serve as indicators of a latent variable. However, in practice, it often occurs that there are convergence problems, that there are covariances between residuals that are not explainable. And so modeling the relationships between the original observed variables appears cumbersome. As a solution, item parceling has been developed. And item parceling is currently a two-step procedure. In the first step, so-called parcels are created, and these parcels are composites of original observed variables. And then in the second step, these composites, these parcels, are used as the indicators of latent variables. Another field of application of composites are formative constructs. Let's start with a quote from Petter and colleagues from the information systems domain. They say, formative constructs occur when the items describe and define the construct rather than vice versa. So here we don't regard indicators or observed variables as consequences of an underlying latent variable, but rather we regard them as ingredients that form something new. And therefore they are part of a definition, and the relationship between an observed variable and the formative construct is rather definitorial. It's not a causal relationship. Examples of formative constructs are socioeconomic status, fear, or core self-evaluation. You always find here the references, so if you're interested in these concrete implementations of formative constructs, feel free to read them. A formative construct is visualized like this, where we have the formative construct eta, and it's defined as being made up out of the observed variables y1, y2, y3. These observed variables are allowed to covary. There's usually no restriction on the covariance between them, and they make up this formative construct eta. When you see this specification of a formative construct, you'll see it is a composite. It is perfectly identical to a composite as we've shown in the very beginning. Well, talking about formative constructs, it is important to notice that the term formative has been used in different ways. Because next to formative constructs, there's also the measurement of latent variables in a formative way. But this is something different. We want to avoid this confusion. Therefore, here we see this difference between formative constructs, or emergent variables as an alternative term for it, contrasted with the formative measurement of a latent variable. Formative constructs are defined by the observed variables. That means the relationship between the observed variables and the formative construct is definitorial, and these observed variables fully explain the construct. In contrast, in formative measurement of latent variables, the observed variables are regarded as causes of a latent variable. So the arrows connecting the observed variable and the latent variables should be interpreted in a causal fashion. And that means there is some variance in the latent variable eta that is not explained by the causes y1, y2, and y3. And that means we have here a residual zeta on construct level. This is the most important statistical difference between formative constructs and the formative measurement of a latent variable. This table contrasts formative constructs with the formative measurement of latent variables. So we do not only have statistical difference between the two, but also conceptual differences. The first obvious difference is the type of construct. Formative constructs are emergent variables. They emerge out of their ingredients. Whereas in formative measurement of a latent variable, we have a latent variable which represents a phenomenon of interest and in the real world. The observed variables have a different role. When we have a formative construct, then the observed variables serve as ingredients, elements, or components, and they make up the formative construct. They define it. In contrast, in formative measurement of a latent variable, the observed variables are causes. They cause the latent variable, and the relationship between the observed variables and the latent variable is a causal one. Then, in both cases, the observed variables are not informative about the amount of measurement error contained in the observed variables. While classically in latent variable modeling, observed variables or the correlation between observed variables are used to gauge how large measurement error is, this does not work with formative observed variables. So if we have the formative measurement of a latent variable, then the correlations among these observed variables do not say anything about the reliability and validity of the measurement of the latent variable. For formative constructs, the same holds. Here, the variables, the observed variables, can correlate highly, but they don't have to correlate highly. Think, for instance, when you bake a cake, and you might bake a cake using sugar, or may bake a cake using honey, and there might be no correlation or maybe even a negative correlation between the use of sugar and the use of honey, but it doesn't say anything about the validity of the resulting artifact. Finally, what happens if we drop an observed variable? If we drop an observed variable of a formative construct, then we alter the recipe. If we leave out an important ingredient of a cake, well, then we'll have a different result. Maybe it's not even a cake anymore if we miss sugar because it's not sweet and it's then rather kind of bread. So dropping observed variables alters the construct's meaning if we have a formative construct. In contrast, if we have formative measurement of a latent variable, then dropping an observed variable only increases the error on construct level. That means the residual variance gets larger, but the meaning of the latent variable does not change. Another field of application of composites are aggregate constructs. An aggregate construct combines or aggregates specific dimensions into a general concept, according to Edwards, 2001. Well, an aggregate construct is depicted here on the right. And we see that we have lower order dimensions, latent variables, that are measured by means of observed variables. And these latent variables make up an aggregate construct. So these latent variables, latent first order constructs, are aggregated on a higher level of abstraction. It's also a special kind of second order construct, where the second order construct is a composite made up of the first order constructs. Examples of this type of model are job satisfaction or operational performance. Another field of application of composites are collections of heterogeneous causes. Sometimes researchers are not interested in the influence of variables individually, but only in the collective effect of a set of variables. So then it is a very straightforward approach to use a composite made up of these individual variables. This composite is not really a phenomenon that has to exist. Rather, it is a tool. It makes the model simpler, so you just look at the effects of the composite and not at the effects of the individual variables anymore. A proponent of this approach is, for instance, Heise, who in 1972 suggests to model a sheaf coefficient, a coefficient that captures the summed effects of a set of variables that one is not really that much interested in.